section 5.4, we're going to look at 3 theorems, and they're all fairly simple. The first one we're going to look at is a theorem that can help us compute when we have integrals that are either even or odd. This first theorem, you never have to use it, but it's a nice trick. So if you have an even function and your limits of integration are opposite, so a negative a to a positive a, you could go ahead and just take 2 times 0 to a. It's always nice to have 0 as one of your limits of integration. If your function is odd and you're going from a negative to a positive a, it's just 0. So recall that a function is even if you replace x with negative x and the y values remain the same. A function is odd if you factor out a negative x and the values are the same. Let's look at these diagrams so we can get a better picture of what this means. Okay, let's say that we're going from this a value, and here we have a negative a value. We wanted to compute that integral. Okay, so this is an even function. Geometrically, what that means is that there's symmetry about the y-axis. So the function is a mirror image of itself. So if we just go from 0 to a, you can see that that area that we're computing will be the same as if we went from negative a to 0. So we can simply go from 0 to a and then just multiply that result by 2. If a function is odd, it's a little bit different. So let's look at the same values. This would be a negative a, and here we have an a. Notice that the function does not have symmetry about the y-axis. It's sort of opposite. So if you look at the region from negative a in this particular example to 0, I'm going to have some negative value, but then the region from 0 to a would be the same. It would just be a positive value. So you can see that if I go from negative a to positive a on an odd function, it'll cancel each other out, because this would be a negative and a positive, and I'll get 0. We're going to use this idea of symmetry in the next example. In example 1, my limits of integration are negative 4 to positive 4. The integrand is x squared minus x to the 4th. Now this is actually an even function. Notice that f of x is equal to the integrand x squared minus x to the 4th, and f of negative x, is equal to negative x squared minus negative x to the 4th, which is simply x squared minus x to the 4th. So I know this is an even function. And since this is an even function, I can just go ahead and integrate from 0 to 4 and then multiply that value by 2 of x squared minus x to the 4th dx. And then that would be 2. This is going to be x to the 3rd over 3 minus x to the 5th over 5. I'm going to evaluate that from 0 to 4. So this would be 2. 4 to the 3rd, I'll figure it out later, over 3 minus 4 to the 5th over 5. And then I'm going to subtract 0 minus 0. Now 4 to the 3rd and 4 to the 5th, I'd have to use a calculator to figure that out. And after I do and multiply it by 2, I'm going to have that this is equal to negative 5504 over 15. let's go ahead and look at example 1b. We're going from negative pi over 2 to pi over 2, so that's kind of a hint that maybe I could use this even or odd function. If I look at my f of x as the cosine of x plus x to the third. Now I know that cosine is an even function, but x to the third is not. Okay, so this is neither even nor odd. However, cosine of x is even and x to the third is odd. So what I could do if I wanted to use this property is break this up into two integrals. The first integral is going to go from negative pi over 2 to pi over 2 of cosine of x dx. And then I'm going to add that to the integral from negative pi over 2 to pi over 2 of x to the third dx. And now here we have an even function. The x to the third is an odd function. The reason being that negative x to the third is equal to negative x to the third. On the first integral, I can use the property of even to integrate from 0 to pi over 2 of cosine of x dx, plus, since this is an odd function, it's just 0. So the integral of cosine is sine. Oops, I'm sorry, 2 times the integral from 0 to pi over 2 of cosine of x. So this is going to be 2 times sine of x evaluated from 0 to pi over 2, which is simply 2 times sine of pi over 2 minus sine of 0. Sine of 0 is just 0. Sine of pi over 2 is 1. So this is simply 2. Again, cute trick, but you don't have to really use that. You can just, oops, went too far. Our next theorem is actually the definition of what we call the average value of a function. Okay, so functions can go from low to high values to low, and they can fluctuate, right? Because when we talk about the value of a function, we're talking about its y values. So what if I did want to find the value of a function? Well, when you think about the area between a function and the x-axis, it's just some sort of number. And what we can do with that area is we can create a rectangle that'll give us the same area as the area below, between the function and the x-axis. Okay? And this rectangle will have some length and some width. So if we were trying to find the area of this rectangle, and if we look at this bottom piece, that would be a length of b minus a, and the width here is just going to be f of x, right? Which would be some y value. And what it is if you look at the curve, that y value is going to be the average value. It turns out that it's the average value of the function. If we wanted to compute the average value of a function, we could use integrals. And the notation is this f with a bar over it. So what we're doing is we're going to compute the average value. We're going to have it equal to 1 over b minus a, integral from a to b of f of x dx. The idea behind this is that, remember that our integral from a to b of f of x dx, that's going to give us some area between the curve and the x-axis. And as we've seen by this rectangle, that area can be written as a rectangle, length times width, where the length is simply b minus a, and the width is that y value. So remember, our area was the value of our integral. So the integral is from a to b f of x dx equal to b minus a times w, where w is just a y value. So if I just go ahead and divide both sides by b minus a, and here this cancels, then I have 1 over b minus a. I have my formula. 1 over b minus a times the integral is equal to the width, where the width is simply the average y value. Now, you'll never have to reproduce that, but it's sometimes nice to know where these formulas come from. Now let's use the formula. If I had to find the average value, so make sure that you read instructions carefully. If you had to find the average value of a function, we could use the integral. Here I have my function. The integral is from -1 to 3, so that would be my a and my b. So I have b minus a is equal to 4. And the average value of the function is going to be 1 over b minus a, so 1/4, times the integral from -1 to 3. F of x is 3x squared plus 7 dx. That would be 1 over 4. 3x squared would be 3x to the third over 3, which is simply x to the third, plus 7x. And then I'm evaluating this from -1 to 3. I have 1/4, 3 to the third, so I would have 27 plus 21 minus -1 minus 7. And that's 48 plus 8, or 56, over 4. What is that? 1? Oh, okay, so that actually reduces to 14. Okay. And that would be the average value of the function from -1 to 3. And integrate like normal. So our next theorem, the last theorem in this section, and this is a pretty short section, is going to be the mean value theorem, but this time it's for integrals. So the mean value theorem for integrals has the condition that the function or the integrand has to be continuous, and that is very important. If it's not continuous, we can't use this theorem. And all it's saying is that if the function is continuous on some interval a, b, then at some point the average value of the function is going to be equal to, at some point, c, f of c. So now if we look at this second graph where it's not continuous, and let's just say this would be the average value of the function, notice that that line does not pass through any of our curves. So here's my curves. So there is no point on this graph where the average value of the function is equal to some value on that graph. So we can't use the mean value theorem here. It has to be continuous. So if the function is continuous, as with this first graph, all it's saying is that if we have this average value, there will be some point on the graph where the function is equal to its average value. Let's look at example 3 and consider the function f of x equal to x to the negative 2 minus 1. We want to find all values in the interval from 1 to 2. So this would be my a would be 1, and my b is 2. So we want to find all the values where f of x is equal to the average value. So remember, the average value is just that f bar on the interval from 1 to 2. Well, first of all, we have to check to see if our function is continuous. Notice that f of x is equal to 1 over x squared minus 1. So f is not continuous when x is equal to 0. However, 0 is not in the interval from 1 to 2. So 0 is not in this interval from 1 to 2. Okay? So we can conclude that f is continuous on the interval from 1 to 2. So again, that's really important that before you use a theorem, you check the conditions. So by this theorem, there's going to exist at least one point where the average value of the function is equal to a y value of the function. First step, compute the average value. In this case, b minus a is 1. So it's going to be 1 over 1, which won't change anything. Integral from 1 to 2, x to the negative 2 minus 1 dx. That's simply x to the negative 1 over negative 1 minus x evaluated from 1 to 2. Or negative 1 over x minus x evaluated from 1 to 2. I have negative 1/2 minus 2 minus negative 1 minus 1, which turns into negative 5/2 plus 2. So the average value of this function from 1 to 2 is negative 1/2. The next step, I have to figure out for what f of x this is equal to the average value of the function. So my function is 1 over x squared. I would rather work with a positive exponent, so I'm going to change the x to the negative 2. 1 over x squared minus 1. I'm looking where that is equal to negative 1/2. And then I'll solve for the x value. Adding 1 to both sides, I have 1 over x squared is equal to positive 1/2, which tells me that x squared is equal to 2. Square rooting both sides, I get plus or minus the square root of 2. But remember, I'm only trying to find x values that are in the interval from 1 to 2. So I would choose x equal to the square root of 2. The negative square root of 2 is not in my interval. Okay, so that is the mean value theorem for integrals. And again, this is a really short section, so we're done with 5.4.